Have you ever pondered what the future holds for space exploration? As we stand at the brink of a new era in space travel, we find ourselves facing a host of challenges, the most formidable of which is propulsion. In today's world, conventional chemical propulsion is rapidly reaching its limits. To ferry missions to Mars and other deep space destinations, we require advanced propulsion technologies, boasting high acceleration, specific impulse, and fuel efficiency. Enter the Magnetic Fusion Plasma Drive, or MFPD, a groundbreaking propulsion concept that may hold the key to our future in space. This innovative device, proposed by Florian Neukart, a professor at Leiden University and board member of the Swiss quantum technology company Terra Quantum AG, merges elements of multiple propulsion techniques to create a system with a high energy density and fuel efficiency that far surpasses that of traditional methods. But why is advanced propulsion so vital? The answer lies in the limitations of our current technologies. Conventional chemical propulsion, while reliable, simply doesn't provide the thrust, energy, efficiency, or longevity necessary for extended missions. This is particularly true for missions to Mars and beyond, where the health, safety, and well-being of astronauts are at serious risk due to prolonged exposure to microgravity and high doses of solar and cosmic radiation. A one-way trip to Mars, for instance, can take up to 9 months, even during the Mars opposition, which occurs every 26 months, when Earth and Mars are at their closest, including surface operations that could last up to a year and the 9-month return journey. Mars missions could last up to 900 days. To overcome these challenges, NASA and other space agencies are exploring alternative propulsion methods. These include fuel-efficient options like electric or ion propulsion, which ionize inert propellant and accelerate it through nozzles to generate thrust. However, these methods typically produce low thrust and rely on large power sources, such as nuclear reactors or solar arrays, to enhance their performance. This is where the Magnetic Fusion Plasma Drive comes into play. By combining ionic and fusion processes, this cutting-edge propulsion system could revolutionize space exploration with its enormous energy density and multiple benefits, despite the challenges of maintaining fusion reactions in space. The future of space exploration may well depend on the success of technologies like the Magnetic Fusion Plasma Drive. As we continue to push the boundaries of what's possible, we move one step closer to a new era of space travel, where our reach is limited only by the breadth of our imagination. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Ever wondered about the major hurdles we face in our quest to explore the vastness of space? One of the biggest challenges is propulsion, the means by which we propel our spacecraft through the cosmos. Today, we're going to delve into the exciting world of space propulsion systems, breaking down some of the most intriguing concepts that could shape the future of space travel. First up, we have solar sails. These ingenious devices harness the power of the sun, using its radiant energy to produce constant acceleration. Imagine a sailboat, but instead of wind, you're propelled by photons from the sun. But there's a catch. Solar sails have to operate closer to the sun and their thrust is limited. Next, we turn our attention to nuclear thermal propulsion, or NTP. This is the brainchild of NASA and DARPA, currently under development as the demonstration rocket for Agile Cislunar Operations, or DRACO. NTP works by using the heat from a nuclear reactor to expand a propellant, like liquid hydrogen, through nozzles, creating thrust. It's an energy-dense system with significant acceleration, but it has its own set of challenges, especially when it comes to safety and handling nuclear materials. Then there are fusion reactions such as deuterium-tritium and deuterium-helium-3. These have been the focus of theoretical scientists for decades. These reactions could power future propulsion systems with very high specific impulse and thrust. But achieving controlled, sustained fusion reactions and managing the required fuel present their own technical difficulties. Let's not forget about more futuristic concepts like the Alcubierre warp drive and antimatter propulsion. These ideas might seem ripped straight from the pages of a science fiction novel, but they are genuine scientific theories. However, don't expect to see them in action anytime soon. Finally, we have Neukart's proposal. This model combines ionic propulsion, fusion propulsion, and other concepts into a system that uses controlled nuclear fusion reactions as its main energy source. The system uses the enormous energy released during fusion reactions to create a high-velocity particle exhaust, which produces thrust. It's a fascinating proposal, but it's still in the theoretical stage. In conclusion, space propulsion is an evolving field with numerous exciting concepts, from solar sails that ride on the sun's radiant energy to fusion reactions that could potentially offer high thrust. These propulsion mechanisms could shape the future of space exploration, but each comes with its own set of challenges and hurdles, be it managing nuclear materials, achieving controlled fusion reactions, or the sheer technical difficulties of more futuristic concepts. Despite these challenges, the quest to explore the cosmos continues, driven by our insatiable curiosity and the relentless pursuit of knowledge. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. What does the future of space travel hold, and what challenges must we conquer to reach it? To answer this, we delve into the realm of aneutron fusion and the revolutionary magneto-inertial fusion propulsion device, or MFPD. Imagine a world where space travel is not limited by the constraints of our current propulsion systems, where the stars are no longer distant dreams, but reachable destinations. This could be our reality with the advent of aneutron fusion. But what is it exactly? At its core, aneutron fusion is a form of nuclear fusion. Think of it as the engine of the sun powering the burning ball of gas and giving it life. But unlike the sun, aneutron fusion aims to generate power with less neutron radiation. Instead of releasing energy through neutrons, aneutron fusion releases energy in the form of charged particles like protons or alpha particles. This drastically reduces the amount of harmful neutron radiation generated, so we have a potential energy source for space travel that is not only more powerful, but also safer. Now let's explore the MFPD system, the vehicle to harness this power. The MFPD system is designed to utilize aneutron fusion, creating a single energy source that provides both thrust and power. This combination of high specific impulse and immense energy density opens up a universe of possibilities. The MFPD system can give a spacecraft a significant velocity change, making trips to distant celestial bodies easier. The high energy density of the fusion fuel can allow for longer missions without requiring large amounts of propellant, and the design may include a lower mass fraction allotted to fuel storage. This frees up more mass for scientific instruments or other technologies. Furthermore, the MFPD system is designed to serve dual purposes, acting as both a propulsion system and an electrical power source for the spacecraft's instruments and systems. This adaptability is key for extended missions. But the advantages don't stop there. The potential for increased continuous thrust could greatly shorten travel times to far-off locations, reducing the danger of cosmic radiation exposure. The system's innate magnetic and physical structures may even offer some degree of radiation shielding. Plus, since the MFPD is independent of solar proximity, it can be used for missions to the outer solar system and beyond. And the cherry on top? The MFPD might be built with a lower risk of radioactive contamination than nuclear thermal or fission electric concepts, since fusion generally uses less radioactive material and may enable safer reactor shutdown. In the grand scheme of space travel, aneutron fusion and the MFPD system offer not just a glimpse, but a roadmap to a future where the cosmos are within our grasp. The journey may be challenging, but the rewards are, quite literally, out of this world. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Imagine a future where we could traverse the vast cosmic distances in a fraction of the time it currently takes us. What could we discover? What secrets does the universe hold for us? The key to this future might lie in the power of fusion propulsion. Our story begins with the birth of an idea, a spark of ingenuity that promised to revolutionize our approach to space travel. Fusion propulsion, a concept that has its roots in the mid-20th century, has always been an enticing prospect. The idea of harnessing the same energy that powers the sun and stars to fuel our journey into the cosmos is awe-inspiring. The journey of fusion propulsion has been marked by gradual yet significant advancements: inertial confinement, fusion and magnetic confinement fusion, two methods of achieving fusion, have seen considerable progress here on Earth. In the former, fusion is contained in the form of plasma using tokamak reactors and magnetic fields. In the latter, Deuterium-tritium fuel tablets are compressed and heated using lasers. Both methods have shown promise and moved us a step closer to realizing the dream of fusion propulsion. However, every story has its challenges, and the tale of fusion propulsion is no different. The primary hurdle lies in establishing and maintaining stable fusion reactions in space. Concerns have been raised about the system's ability to manage the heat generated by reactions, the subsequent radiation, and the structural implications for spacecraft. But these challenges are not insurmountable. And so, we find ourselves at the precipice of a new era. The development of the Draco demonstrator signifies that nuclear tests in space are already underway. Fusion propulsion is not a distant dream, but a tangible reality that we are inching closer to every day. The potential of fusion propulsion is immense. It promises to revolutionize spacecraft design, providing propulsion and electrical power simultaneously. It could mitigate the risks of long-duration space missions, such as exposure to radiation and microgravity. It could enhance our capabilities for human exploration. But beyond these, it could also inspire technological spin-offs in materials, science, plasma physics, and energy production. The road to fusion propulsion is fraught with challenges and scientific roadblocks, but the payoff is enormous. If successful, it could push the boundaries of what is possible and usher in a new era of space exploration. It could allow us to chart our future among the stars, inspiring curiosity, inventiveness, and resolve in scientists, engineers, and explorers around the world. So as we stand on the cusp of this new era, we remember that every great journey begins with a single step. The journey of fusion propulsion is no different. It is a step we are ready to take, a step into the future. A future where the stars are not just points of light in the night sky, but destinations waiting to be explored. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content.